All right, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. Thank you guys for your flexibility today. So I'm a little sick, so that's why I'm teaching from home, like I mentioned last Wednesday. How's everyone doing today?
Pretty good.
Good to hear. Okay. All right, and so for today's lecture, the plan is to finish up our lecture notes on gait biomechanics, and so we're going to talk a little bit about kinematics today, and then spend the rest of the time talking about running. Okay. And so that'll kind of transition us into our next topic, which we'll cover on Wednesday, which is muscle dynamics. Right? Okay, so a couple announcements. So I did post homework 4 last week, so that is up online. Should be a pretty quick homework. I don't think it'll take you too long. A lot of it's based on the gait biomechanics that we're talking about now, and a little bit based on the muscle biomechanics that we'll go over on starting Wednesday, and then continuing on into the next week after that. So I think you have until basically the end of October to get that done. So I think the due date is October 27th. Okay. Okay. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. And so the first thing we're going to talk about today is biomechanical kinematics. Okay. Okay, so we're starting this new unit now on human dynamics, right? And dynamics, have movement that's associated with them, right? That's why we call them dynamics, and not statics. And so anytime you have any kind of movement or any kind of motion or moving objects, one of the first things we have to talk about is kinematics, right? Okay. So I think I mentioned this briefly when we started talking about gait mechanics in general, but kinematics, I always like to think of it as kind of like the language of describing motion. Okay, so these are all the kind of the terms, the concepts, the definitions that we use to kind of describe motion, right? Because anytime you have any kind of phenomenon, whether it be scientific or even just anything out in the real world, right? We need kind of a standard way to kind of describe things and quantify things so that everyone's kind of on the same page in terms of understanding kind of what we're all talking about. And so kinematics kind of provides that kind of baseline language or baseline definitions for us to do that. Okay. And so the definition of kinematics is just basically a way to describe motion using kind of a systematic kind of consistent language. So that's true in general. And so when you talk about whether you talk about biomechanical kinematics or Newtonian kinematics or or Lagrangian or whatever, right? So kinematics is all the same. When we talk about specifically biomechanical kinematics, obviously we're talking about kind of motion of the body. And so and then that kind of raises the question of how do we describe motion of the body? Well, the way that we typically do this is that we measure the angles of the joints. Okay. And as the body goes through its motions, these body angles are going to change. These joint angles are going to change as a function of time. Okay, and so a lot of what we measure, a lot of what we we quantify are just how these angles change, as the body goes through a particular motion. Okay. Okay. And so let's look at a couple of examples from walking, right? And so we've, last class we talked a lot about the different stages of walking, right? We have the different phases. We have the stance phase, the swing phase, the double support phase, things like that. And so as the human body goes through those different phases of walking, each of the different joints in the lower body are going to go through different periods of flexion, extension, and so we can measure those with their joint angles. Okay. Okay. Let's look at the example of the hip joint during walking. Okay. All right. So typically we measure these in a graph like this. Okay. And so on the horizontal axis we have time. Usually we measure that in seconds. Okay. And then on the vertical axis, what we measure is an angle, right? And so, we're basically measuring the flexion of the hip at this point. Okay. And so as a person's walking, let me go ahead and draw you a figure, right? Okay. The hip flexion angle would be this angle right here. Okay. And so the hip flexion angle is the angle of the hip joint, which is the angle between your thigh and your pelvis. Okay. And we're basically measuring that as a function of time. Okay. And so if we measure that, let me go ahead and draw a dotted line here as well. Okay. So this dotted line here will correspond to kind of a neutral position. Okay. And so what we can say is that anything above this line will be the knee is in flexion. And then anything below this line, the knee will be in extension. Okay. All right, and so the curve for the hip flexion angle as a function of time for walking looks something like this. Okay. And so then the hip starts usually flexed, and then it goes down. Okay. During the stance phase, because when you're in the stance phase, your foot is planted on the ground and your hip is kind of maximally extended. Okay. And then as you kind of push off the ground and as you go into the swing phase, kind of comes back up here like that. Okay. And then of course, this starts to repeat because then that goes into the next cycle. Okay. And so right here, kind of right when we kind of transition from extension to flexion, this is when your toe comes off. So this is the end of the stance phase. Okay. And then that cycle just kind of repeats. Okay. Okay. So this is a pretty typical graph that you'll see, when someone's talking about human kinematics. Okay. And so you want to graph basically these joint angles as a function of time. Okay. Okay. Any questions on this? Okay. All right. And so we're going to get into kinematics, not next week, but probably the week after that. And so you might be wondering how this is measured, and it's actually a very interesting way. And it's actually, a big topic what we're going to talk about. So traditionally, the way these were measured was that, someone, usually took a video recording of someone going through a motion, and then you kind of measure the angles as a function of time, right? And even before that, kind of, before the age of kind of digital pictures, digital videos, people would wear kind of devices that would kind of track, these angles as a function of time. Okay. Nowadays, the state of the art is to use actually motion capture technology to measure these things. Ooh, excuse me. Ooh, excuse me. Okay. If you're unfamiliar with motion capture, well, first of all, some of you may have heard of it before because a lot of digital art and digital media uses it in creating their art. And so, for instance, now computer graphics is kind of a big thing, but in the past, when movies like Toy Story and and Finding Nemo came out, right? Disney Pixar was kind of the leader in this kind of technology. And so to kind of create more realistic looking motions and more realistic kind of, actions, what they would do is that they would put their actors into motion capture suits and actually measure them actually acting out certain scenes. And then what the movie studios would do after that was then they would kind of overlay the computer graphics character, whether it be, Woody, Buzz Lightyear, Nemo's dad. I always forget Nemo's dad's name, but he's always just Nemo's dad to me. I think his name is Marlin or something. And then they would, and then when they animate that, when they render it, it looks like a much more believable kind of human expression and human motion because they were modeled after they were captured from a real person. Although what you actually see on screen is still a cartoon character. And so video games make use of this technology as well for similar reasons. But besides the art, besides art and entertainment, there's a lot of really cool kind of science applications for motion capture as well. And so nowadays, when people are kind of studying human motion, whether it be athletes or whether it be people that are struggling with a disability, right? A lot of times, scientists will have these patients or these people come into a motion capture lab and actually measure them, going about their daily business. They have them walk, right? And then based on the motion capture sensors, the motion capture technology, they'll be able to get readings like this. And so it's becoming much more ubiquitous, and there's been a ton of money, a ton of investment in that area, and it's actually something that actually gets better and better all the time. And so, we're going to talk a lot more about how this works and how to do some elementary calculations with it, probably in a couple weeks, because it's kind of a big part of how human biomechanics are analyzed nowadays. Yeah. Okay, so let me draw a couple more graphs for you just so that you kind of have an idea of the different joints. And so far we've done the hip angle, the hip flexion angle. Let me show you the knee flexion angle as well. Okay, so same thing. Our horizontal axis will be time, typically measured in seconds. And on the vertical axis, we have angle. Okay, so the knee kind of does an interesting thing. And so, as the graph goes up, that's when the knee is kind of flexed more, right? And so during the stance phase, right? So kind of after your foot kind of touches the ground, your knee actually flexes a little bit because you kind of have to bend down a little bit during the stance phase. And then as you kind of push off, then your knee kind of straightens out again. And so what you're going to see is kind of an initial phase of flexion. So this is kind of your knee flexion during the stance phase. Okay. Then as you start to push off, okay, your knee kind of enters kind of a second phase of flexion that goes kind of much higher from there. And so the end of stance phase kind of occurs right around here. So this right here is about toe off. Okay. And then during the swing phase, your foot is off the ground, but in order to make sure that your foot clears the ground as you kind of swing forward, then your knee has to flex a lot more, right? Because if you kind of, if you take a step and you keep your knee straight, your foot is going to hit the ground. And so to kind of make sure that your knee kind of comes up out. I bang my knee on my desk. And so to make sure that your whole leg clears the ground and you're able to kind of to take the next step, your knee has to flex a lot in order to make sure that you get that proper clearance. Okay. Okay. All right, and then finally, let's look at the ankle. So the ankle actually does quite a few things, and so it kind of goes through different stages of kind of dorsiflexion and plantar flexion. As your foot kind of touches down, as you go through the middle of stance phase, as you push off, and then during the swing phase as well. Okay. All right, so just like the hip, let me go ahead and draw a 0 here. And so on top of this line, we'll have dorsiflexion. And on the bottom of the line, we'll have plantar flexion. Okay. And so the ankle kind of goes through different phases. And so, for the most part, it kind of oscillates around kind of 0 or its resting position. And so for the first part of stance phase, you're going to dorsiflex a little bit because right when you kind of touch the ground or right before you touch the ground, typically your foot kind of dorsiflexes as you kind of absorb that pressure from stepping down. Okay. Then you're going to plantar flex a little bit as you kind of your foot kind of fully rests on the ground, your heel kind of touches the ground, things like that. Then you go through dorsiflexion again. So this is a little bit of a prolonged period. And then right when you touch off, or right when your toe comes off, you go into this huge kind of plantar flexion stage right here. Okay. And so toe off is approximately kind of right here, right before it kind of dives down into that, right before it kind of dives down into that kind of big plantar flexion phase. Okay. Okay. So these three graphs here are kind of, three examples of how you can quantify the kinematics during walking. Okay. Of course, these don't tell the whole story because, there's a lot more to the motion than just, than just three joints. In fact, these three graphs here, you can kind of consider them to be 3 degrees of freedom. So three variables to describe walking. In reality, in order to kind of fully capture walking in its entirety, you need 16 degrees of freedom. Okay. That's because, in addition to kind of hip flexion, you also have kind of hip abduction, adduction, and so that's another degree of freedom. You have the position of the center of masses for each of the body parts, and so there's a lot. And so in reality, when you talk about kinematics, you're usually talking about fairly highly dimensional systems, and so systems that you can't just describe with just 2 or 3 degrees of freedom. But with that said, with a lot of motions, there's usually some degrees of freedom that are what I call kind of predominant. And so those are the ones that are most noticeable and it kind of comprise the majority of the motion. And so I would say for walking, these three right here, hip flexion, knee flexion, ankle flexion, these are kind of the 3 dominant degrees of freedom that are associated with walking. Okay. But just know that in reality, there's a lot more complexity in this, and then there's kind of a lot deeper that you can dive into in terms of measuring the kinematics. Okay. And then the next thing after kinematics is of course dynamics, and so kinematics is the first step. The second step is kind of asking the question of okay, now that we have this motion, how do we actually get to this point? How do we produce this motion? What are the forces and what are the moments, the torques that produce this motion? Okay. And so usually from data like this, a computer, most of the time it's a computer will run through some calculations to tell you, like the calf muscle or the quadricep muscles, exerted this amount of force as a function of time. Okay. Because ultimately, getting that information about the muscles and the joints, that's usually what's most useful in terms of, either a medical diagnosis or doing any kind of analysis or maybe just a design of some biomechanical device. And so, getting that information, extracting it from the kinematics is key. Okay. All right. Any questions on this? Okay. All right. So let's go ahead and move on to running then. So that's everything with walking. Let's talk about how people run. Okay. All right. So just to kind of summarize how walking worked, right? So in when we talked about kind of its kinetic and potential energy, we talked about walking as kind of mostly a passive thing, right? Even though your muscles are doing stuff, your bones are doing stuff, your joints are experiencing forces, most of those forces are mostly due to just, just supporting the weight of the body. Okay. Okay. All right. Running, of course, is going to be the opposite. So running is a lot more active, right? And when you see kind of graphs of its kinematics, you see graphs of its kind of its energetics, its dynamics, you'll start to see kind of why. And so your muscle, and so the way that it's more active is that your muscles are a lot more involved when you're running than when you're walking. Okay. Okay. So let's start by talking about the different stages of running. Okay. All right. So it's similar to the walking gait cycle, except we call things a little bit differently in running, and of course because we're running, we have different stage, we have different things that will happen as well. Okay. Okay. So let's go ahead and give it a shot. Okay, so we're going to start. So running is a cycle, and so it's something that's kind of repeated over and over again. But we have to start somewhere, and so we're going to start right at the foot contact event. So right when your foot kind of touches the ground, we'll start there, and then we'll describe the stages from there. Okay. Okay. So foot contact kind of starts like this. Okay. And so just like before, I'm going to focus mostly on just one leg, and then the other leg will kind of be dotted in the background. And so you can think of the other leg kind of doing the same thing as our featured leg, just kind of out of phase from the featured leg. Okay. Okay. So here we have a foot contact. Okay. Right. And then from foot contact, the next stage or the next event that we usually measure is when your foot kind of comes off the ground. And so you kind of taken a step. Okay. And so it's just like this. Okay. Okay. So remember, the foot that we're looking at, or the leg that we're looking at, is in the back this time. So this is a toe off. Okay. All right. And so from toe off, there's a period of time, like we mentioned before, where neither foot is on the ground. And so you're basically almost kind of flying for a second. So this is called the flight phase. Okay. So flight phase kind of looks something like this. Okay. So your other foot is about to touch down, but it's not quite there yet. Okay. Okay. And then after flight phase, your off foot touches the ground. And so at this point, your leg that's in the back, you're going to bring it forward to take the next step. And so, just like we talked about in walking, in order to do that, your knee has to flex a lot in order to clear the ground as your hip is kind of swinging it forward. Okay. And so the next phase, what we have is called peak knee flexion. Okay. And so that looks like something like this. Okay. And so your knee is flexed, you're bringing your leg forward. Okay. And then as you kind of prepare that foot to step down again, your knee becomes unflexed, and then it's about to hit the ground. And then finally you have your next foot contact event, and you kind of start the whole thing over again. Okay. Okay, so those are the various phases of the cycle. Okay, and so let's kind of break down, how long your foot kind of stays in contact with the ground relative to walking. Okay, and so with walking, if you remember correctly, there was about a 60-40 split. So 60% of the time, one given leg is on the ground, and then 40% of the time it spends in the air, okay, or during the swing phase. And so here the numbers are kind of opposite a little bit. Um, and so during this entire time right here, okay, we call this the stance phase. Okay, and so during the stance phase, that foot that we're talking about, or the featured foot, is on the ground. This is comprised of about 35% of the running gait cycle. And the rest of the time is the swing phase, and so that's the phase when your one leg is off the ground. And this is comprised of about 65% of the time. Okay. All right, and then what's unique about running is that instead of having a double support phase where both feet are on the ground, there's a phase where both feet are off the ground. So we call that kind of the flight phase. And so flight is maybe right here. Okay. And this is about 15%. Okay. So about 15% of the running gait cycle, neither of your feet are on the ground, and you're literally just kind of flying. Okay. Okay. So let's talk about some numbers a little bit. So let's talk about some typical speeds. Okay. 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 So there's various kind of intensities of running, and so anything from kind of a light jog to a full-on sprint, all of those are considered running. They all kind of have the same biomechanics, the same motion. And so when I talk about typical running speed, what I mean is kind of a typical, I would say, moderate running speed, which is kind of not a light jog. It's more of a brisk jog. Think of it like that. Okay. So you're definitely not all out sprinting, but you're not super casual about it either. And so you're jogging, you're trying to get somewhere fast, but you're wearing a nice suit and your hair is really nice, so you don't want to sweat too much. And so that's how I typically think of a kind of a typical moderate run. Okay, so this speed is about 4 meters per second for the average person. Okay. All right, and so the other thing that speeds up as well is your cadence, and so the frequency at which you kind of make steps. Okay. Okay. And so this is about 180 steps per minute. Okay. So you can see here that you're taking about 3 steps, 3 steps per second, right? Because we have 60 seconds per minute, and so 180 steps per minute is 3 steps per second. So still fairly fast. Okay. And the step length is about the same. So usually when people are running, they don't really extend their legs all too much compared to walking. So that is about 1.3 to 1.4 meters. Okay. So that's the running gait cycle. So we're not going to dwell too much on this just because we've already defined a lot of these terms when we talk about walking. But I did want to kind of make you aware of the different phases and kind of the different breakdown of the phases. Okay. All right. Any questions on this? Okay. All right. And so next thing we're going to talk about is the energetics or the dynamics of running. Okay. Okay. Okay, and so we can measure these in the same way. And so if you recall from walking from last Wednesday, what we essentially, or the way that this is typically measured is that usually someone will, or a scientist will ask a runner to run on a force plate, and so the force plate will measure the ground reaction forces, and then based on the ground reaction forces, we can integrate these to get things like position and velocity, and then we can compute kinetic and potential energy. Okay. 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 And so if you remember kind of, after we kind of went through this exercise with walking, what we saw was that the kinetic and potential energy were out of phase. Okay. And so when you're walking, you go through different phases of, potential energy is maximum during stance phase, and then kinetic energy becomes a maximum during swing. And then these two are kind of, both oscillating and they're kind of going up and down at different times. Okay. Hence, that's why we kind of mention to say that, walking is mostly passive because the raw amount of energy in the system is roughly the same. Okay. With running, we don't see this. Running, we actually get the opposite. Okay. Because of the way the different phases are kind of overlapping each other, what we actually see during running is that the kinetic and potential energy are actually perfectly in phase with each other. And so they're like kind of almost overlapping sinusoids. Okay? And so it looks kind of something like this. All right. And so on the horizontal axis, we have time measured in seconds. And on the y-axis, we have energy. Okay. All right. And so the potential energy, maybe looks something like this. Okay. It oscillates up and down because, running it undergoes different cycles. Okay. Okay. And so as you run, your center of mass is going to go up and down, as you kind of step down, you push off, step down, push off. Okay. Meanwhile, your kinetic energy is going to be doing the same thing. And so I'm going to draw it a little bit lower, so you can kind of differentiate the graphs. That's not to say potential energy is usually higher than kinetic energy. It's just, for this graph, I just happened to draw the potential energy one first. But, the more important things to see, that these two graphs are actually in phase. Okay. Okay. But of course, depending on how fast you're going, how quickly you're sprinting, your kinetic energy might actually exceed your potential energy, and so it kind of depends on the magnitudes of your running. But I drew them kind of slightly offset just so that you can see them. Okay. Okay. And so if you're kind of wondering kind of, where these peaks and valleys they correspond to, the peaks here, they represent kind of the middle of the flight phase. So that's kind of when you're at your maximum velocity. So when both your feet are off the ground. Okay. And then the valleys here, these kind of correspond to mid stance phase. And so that's kind of when you're at kind of the lowest of your stance phase, you're just about to push off. And that's when kind of both energies are kind of at their minimum. Okay. Because your foot's on the ground. And so because your foot's on the ground, it kind of slows you down a little bit. Because you're not kind of in the air. Okay. And so you have kind of a backwards kind of force being applied to you. And then your potential energy is also the lowest because you're on that one foot, you're bending down, you're almost kind of do like a mini jump, right? And we'll talk about kind of why that's important in a second too. So this right here is kind of mid stance. Okay. Okay. And so like I mentioned, both of these energies are perfectly in phase with each other. Okay. That means that we have a very different mechanism for running here, right? Because what we kind of the argument that we made during walking was that because the potential and kinetic energy were out of phase, right? As your body kind of goes through the walking gait and kind of propels yourself forward, one way that we could interpret that was just kind of a very simple exchange between potential energy and kinetic energy, right? And so if potential energy was highest, then kinetic energy was lowest. Okay. Then as you kind of go through the next phase, right? And you're kind of mid step, okay, or mid swing, then your kinetic energy will be the highest, but then your potential energy will be the lowest. Okay. And so the total amount of energy that's in your system during walking is roughly constant. And you're kind of just exchanging energy between those two pools to move yourself forward. Okay. Now we have a very different mechanism because these two energies are in phase. We can't really say that our energies here are constant because our total energy is going to go down when both the potential and kinetic energy go down, and they come up and down here. Okay. Okay. And that different mechanic is that as you kind of go up in kinetic and potential energy, that energy has to come from somewhere, right? So that that energy doesn't just come from nothing, right? And so that kind of spike in energy or that rise in energy, a rise in total energy of your entire body comes directly from your muscles, and so your muscles are kind of providing that work or that energy to kind of propel yourself forward. Okay. Okay. Hence, kind of why I describe running as a lot more active because your muscles have to kind of, not only support the weight of your body, but also kind of actively kind of supply energy, actively do work in order to, give the energy that's necessary to go through this gait cycle. Okay. And so then, that kind of begs the question then is, that kind of explains why the total energy goes up. But what happens when the total energy goes down, right? So where does that energy go? Kind of funnily enough, it actually goes into your muscles as well, because as you kind of run and as you step down, remember like we talked about, a big part of walking and running is that when your foot steps down, you kind of have to stop yourself a little bit. You kind of have to brake and reduce your speed, mostly to ensure balance and to make sure that your foot kind of gets good traction on the ground. And so when the total amount of energy comes down, when that potential and kinetic energy go down, that gets, not really absorbed by your muscles, but they kind of get lost in friction because, as your foot kind of touches the ground, there's some friction between your foot and the ground that gets lost. There's some kind of, deformation energy that kind of goes into your muscles breaking, and so your muscles, even though they add energy during the push off during the right before flight, they also kind of take away that energy to purposely slow yourself down in kind of the early stance phase. So just so that you don't go tumbling on top of yourself, and you don't slip and fall. Okay. So yeah, so it's kind of a double whammy for your muscles. They have to kind of exert energy to propel yourself forward, and they have to exert energy to kind of slow yourself down during the stance phase to make sure that um, everything stays balanced. Okay. Okay. So running relies, much more heavily on your muscles, and that's generally true for a lot of kind of human motions, or at least human motions that we're kind of interested in from a scientific perspective. We're interested in kind of how much energy that your muscles are exerting. Okay. All right. Any questions on this? Okay. All right, and so because the mechanisms or because the energies in running are a lot different than walking, that kind of implies that we should maybe come up with different models or different analogies. Okay, and so when we talked about walking, we talked a lot about a pendulum, right? So what was the argument we were making was that a pendulum, at least mechanically, is very similar to walking because the pendulum kind of has that exchange of potential and kinetic energy. Okay. So that's no longer going to be valid here. And so when we're talking about running, even though it's still, usually it's still the same person, right? Generally, we're studying the same people. Um, but biomechanically, it's a very different kind of motion. And so our model should also change to kind of account for that. Okay. And so a very simple model or very simple analogy that you can make to describe running is actually using a spring. Okay. Because now we have this kind of increased notion of the muscles kind of providing energy, right? Um, and so, a spring is kind of a great analogy for this, right? We've already talked about how muscles kind of mimic the properties of an elastic solid in a previous chapter, kind of way back when. And so, this kind of relies on that kind of same analogy. Okay. Okay. Because as a person kind of steps down, right? One way that you can kind of think of this is that that's almost kind of like a spring storing energy, and then when your feet kind of push off and go into the flight phase, that's almost like the spring kind of releasing that energy to kind of propel yourself forward. Okay. Okay. And in fact, some of the very early kind of attempts at modeling running used what's called basically like a hopping robot. So it's almost kind of like a pogo stick with just a little bit more a little bit more sophistication. Okay. And so this is from the 80s, and so this was done by a scientist named Mark Rybert. I think that's how you pronounce his name. And so the basic idea was like this. And so he basically took a pogo stick and he put just like a balance beam on it. Okay. And so it looked kind of something like this. And so he had a okay. And so this right here is basically this box right here kind of represents kind of an adaptive spring. And so it's kind of a spring that you can kind of control. Okay. And then at the bottom of that, we had a foot. And so something that was kind of a lot easier to kind of, make contact with the ground and stay balanced. Okay. Right. And then to kind of mimic the effect of the human body, kind of providing in this case, is providing a counterweight. He added kind of a beam with weights on it. Okay. Okay. And so we call that the balance beam, although it's not, of course, it's not the same balance beam that you kind of associate with gymnastics. And so it's literally a beam that's there for balancing the robot. Okay. And so what this guy did, or what these early attempts kind of attempted to do, was that this right here, what I'm showing you, was kind of in the early stages of stance. Okay. And then as a person kind of rotates their hip or flexes their hip and then pushes off, this robot is also going to do that as well. Okay. And so the idea is that, as you go through the gait cycle here, you know, the robot may push off. Okay. So maybe this, maybe this right here is the robot kind of leaves the ground. Okay. And then right here, we are in flight. Okay. Again, with the balance beam. Okay. And then as it comes down, it starts to kind of put its leg forward during swing, and then it kind of makes contact with the ground again. Okay. And the cycle then just kind of repeats from there. Okay. And so it literally looks like a pogo stick, right? And so it's you kind of push off with one leg, it hops, and then it lands again, and then it rotates and then hops, and then and then the point of the balance beam is just to make sure that this pogo stick can kind of stay balanced. Okay. Right. So obviously, very, very simple model. Maybe visually you might look at it and say that that looks nothing like running at all. But it at least kind of captures the same essence of running, and the fact that we have a spring. You compress the spring. When you compress the spring, kind of the overall energy in the system kind of goes down. Then as the spring exerts, it does work on the system, and so you kind of reach the peak of potential and kinetic energy at the same time, and then you kind of repeat that process. Okay. And so at least from an energy point of view, this robot actually does a decent job of mimicking the biomechanics. It's just that practically, it's practically useless because, there's besides entertainment, there may not be much use for a hopping robot. Okay. Okay. Any questions on this? Okay. So yeah, so that's kind of another really interesting model that's kind of come from these studies. Okay. Another really interesting application. So, this is kind of, looking ahead quite a bit. And so, this is kind of a very kind of specific application, but kind of knowing that this fact, or knowing the fact that, we can take running and model it as a spring, even that just simple model, or even that's just simple mindset, can be used for very interesting kind of engineering application, right? In particular, someone kind of took that train of thought and kind of took that mindset and say, can we design better running tracks for people based on that knowledge? Okay. So I call this kind of the tuned track. Okay. And so I think, hopefully everyone's been on like a running track before, either in high school or maybe maybe you visited the one here at Cal State Fullerton, right? But the idea with the running track is to kind of provide a venue or a place for people to do kind of, either races or to do training or to do jogging and things like that. Okay. And so kind of the conventional wisdom kind of back in the day regarding these tracks was to try to minimize the amount of time that the foot spends in contact with the ground. Okay. Okay. Because usually, for a lot of these tracks, runners are usually going for their for speed, right? And so they, whether it's a short sprint or a long distance run, right? Runners want to be able to achieve better and better speed, right? And so that's part of the reason why you come to a running track, to try to push yourself and see how fast you can run a mile or 2 miles, something like that. Okay. And so to kind of maximize this performance, the conventional wisdom is like, all right, we want to minimize the amount of time that the foot is on the ground, okay? Because I think people were kind of thinking kind of the opposite of what you would think of if you were running on like the beach or something, right? And so I think someone mentioned last time that when you're running on sand, it's a lot slower for you to run because you spend so much time kind of you're digging your feet out of the sand, and that kind of dramatically reduces your speed. And so, kind of the idea back then was to kind of do the exact opposite of that. And so, to try to minimize your contact time by making the track as hard as possible. So the idea was, make the track literally made out of concrete or the most kind of hard material, so that when your foot comes down, it will literally kind of bounce off it immediately and not spend any time, for the track to either compress or kind of absorb your impact. Okay. Okay. So that was conventional wisdom before. But if you've ever seen like a modern running track, you either watch the Olympics on TV, or you can even go to the running track here at Cal State Fullerton. I actually haven't been to the one at Cal State Fullerton, but I think I've seen pictures that a lot of times you kind of see this. It's not really concrete, but it's kind of almost this kind of like brown. Most times it's brown, kind of almost like kind of it's like a little squishy. And so if you kind of walk on the track, it doesn't feel like you're stepping on concrete. It feels like you're kind of walking on something that's has a little bit of give to it, right? And so if you ever wondered why that is, part of it is injury mitigation, right? And so if you're running on a very hard, compact surface, there's a lot of research that's out there that says you're putting yourself at risk for things like shin splints, things like stress fractures and things like that. So part of it is injury mitigation. But actually, having a slightly softer surface can actually maximize your performance as well. Okay. And so what scientists were seeing was that, as these kind of softer tracks, start to become developed, what they were seeing was that runners were actually achieving kind of shorter times and faster times on these softer tracks relative to the very, very hard tracks. And so that got people thinking of, why was this? Why was these kind of softer tracks, not only reducing injury, which is probably the most important thing, but also kind of maximizing performance as well. Okay. Because you would think that if you have a softer track, you would think that it would almost kind of be like you're running in sand, right? And so that's usually a bad thing. Well, scientists start to justify it based on this kind of very simple model that we have here, that running is very similar to compressing a spring. Okay. And so you can draw kind of this kind of very simple model of a foot. Let's draw a diagram of a foot being in contact with the track, but we're going to replace the foot with kind of a mass spring system. Okay. And so if we were to draw this diagram, it would look maybe something like this. Okay. Okay, so this is someone's leg with an abnormally huge foot. So let me draw it with some thickness here. Okay. All right, so that's someone's sneaker that they're about to make contact on with the track. Okay. If we use this analogy, if we use this model of the foot being represented by a mass spring, we can draw an equivalent system that looks like this. Okay. So let's say that we have a mass here. Okay. So this mass M might represent the mass of the total human body. Okay. And then true to our model for running, the motion of this mass is going to be dictated by, the spring constant that's associated with your leg muscles. Okay. Right. So that's what we have there on the left. And so on the left there, we have a spring with its associated spring constant. Okay. Your leg, of course, isn't exactly like a spring, but if you take enough measurements, you can get what I call an effective spring constant. And so, it's not the spring constant in the way that think of a spring, but in order to kind of mimic maybe the same behavior, mimic the same kind of energy profile, the same kinematics, we can represent it by an effective, what we call an effective spring constant. Okay. Okay. So I want to make that clear. So it's not actually a spring. So you don't have a coiled spring inside your leg, but we can kind of represent your leg as such. Okay. So it's a simplification, but it's one that's kind of useful in this setting. Okay. Okay. And then the other thing that we can use to model your leg here is a dash pot, and so that's to represent some kind of either viscous damping or frictional damping. And so, like I mentioned before, that whenever you have kind of a mass spring system like your leg, there's some energy loss that's associated with kind of slowing yourself down, braking, restoring balance, things like that. And so, whenever you have kind of an energy loss mechanic, you can represent that with what's basically called like a dash pot. Okay. This right here is a dash pot. Okay. Most physical systems have some degree of energy loss, whether it be heat loss from friction, air resistance. There's always some degree of energy loss. It's just that sometimes it's more significant than others, but it's always good to include it. Okay. Okay. So that's the mass spring system that's comprised of your leg and the rest of the body. Okay. Um, but what scientists found was that if we represent the track as a spring constant as well, okay, okay, where this K track here kind of represents the elasticity of the running track. Okay, right? Because if you have a squishy track, that's one another way that you can model that is as was with the effective spring constant as well. Okay. Because if you think about it, if you have kind of a squishy track or squishy anything, right? If you push it down, eventually it's going to come back to its original shape, right? You push it down, it comes back. Push it down, it comes back. Anytime that you have that kind of behavior where you have some kind of internal forces that want to restore your whatever object it is to its original state, that's kind of elastic properties. And so whenever you have something elastic like this, you can represent it with a spring. Okay. Okay. And so if you have a system like this, this is really good because we've basically taken kind of a fairly complex system of someone running on a track that doesn't have that's kind of squishy to a degree, and we've represented it using these kind of variables and these components that everyone's kind of seen in their engineering classes at some point. Okay. And so now that we have this model, we can write out its governing differential equations or governing equations and then analyze it mathematically from there. Okay. And in fact, whenever you have equations, you can kind of manipulate those equations, or even better, optimize those equations, to optimize a certain behavior that you want. Okay. Okay. And this system in particular is fairly simple because it's basically just a two spring system. So you have two springs and a mass, right? And so you have basically two governing equations that are based on F is equal to ma. Okay. Okay. And so one thing that we can optimize here, or the thing that we want to optimize, because remember, the reason we kind of started this whole journey was to try to make it to maximize the performance of a runner. Okay. And so we want to basically minimize the amount of time that the foot spends in contact with the ground. Okay. Okay. All right. And so you can go through that mathematical procedure. You can run an optimization algorithm or an optimization framework. Okay. And if traditional wisdom held, right? Because remember, traditional wisdom basically say that, if you make the track as hard as possible, you make it as stiff as possible, then what we should see is that, that if we maximize K track, and so if the spring constant of the track is maximized, and so if we basically set it to be infinity, ideally that should be the thing that minimizes contact time. Okay. But that was not the case, right? And so after performing this relatively simple analysis, what scientists found was that there are intermediate values for the track spring constant that actually minimize contact time. Should be K track. Sorry. Okay. Right. So that was kind of a pretty surprising result for a lot of people because kind of conventional wisdom, right? And so if you bounce like a bouncy ball, off the ground, it'll bounce much higher off concrete than say like sand, right? You may not even get any bounce off sand. But from this analysis, what scientists were able to find was that there are maybe it's not maybe you're not supposed to have a hard really hard track. You should have some give to it to kind of maximize runners' performance. Okay, and if you're curious of the reason why, I have a little bit more explanation in the lecture notes. Unfortunately, we don't have time for today, but it has to do with kind of minimizing the natural frequency of the system. So basically, you want to set basically the ideal stiffness for the track is one that kind of closely mimics the stiffness of a person's leg or the average stiffness of a person's leg. Because if you do that, then you're basically going to have a system that's critically damped, and then you kind of minimize that natural frequency, which will then allow that leg to kind of push down, step down, and push off, kind of in the most natural, fast way possible. Which not only kind of minimizes contact time, but also gives the foot kind of a little bit of energy when it pushes off as well. Okay, and that's what kind of leads you to having better performance on these tracks, rather than running on concrete. And running on concrete is usually kind of bad for you anyway, because you're going to end up with a lot of injuries that way. So if you do a lot of long distance running, usually the recommendation is that if you have access to a running track, that's usually the best way, just because that surface was engineered specifically to make sure that you get better times, and to kind of reduce your injury risk. But otherwise, it's better to run on stuff that's not concrete. So either grass or dirt or something that has a little bit of give, just to kind of make sure to kind of preserve your legs for the long haul. Okay. Okay. Any questions on this? Okay. All right. So one last thing that I want to talk about today is to kind of it also kind of builds off this analogy of your legs being represented by a spring, right? And so what scientists were curious about is that how does the effective spring constant for the leg change between different species of animal? Okay. Right, because no matter the species of animal, there are going to be periods of time in an animal's life where it's going to be running, it's going to be sprinting, right? Whether it's for survival or whether it's for getting for food or something like that. Okay, twice a day, no matter where my cat is in the house, once her feeder goes off, she will sprint up to her feeder, and that's literally the most amount of exercise that she gets every single day. So even a very domesticated house cat, makes use of sprinting. Okay, and so the question, it kind of begs the question of how does leg stiffness kind of vary with animal species? And so there's actually, kind of a direct correlation, with kind of the more massive an animal is, the more it weighs, the stiffer the legs are. Okay. And the stiffer the legs are, that's associated with kind of a loss in flexibility or a loss in mobility. Okay. And this kind of is consistent with kind of what what we kind of intuitively know as well. And so if you think of kind of like a very, very massive animal, like say like an elephant or a giraffe or something like that, we don't think of those animals as being particularly mobile or being particularly flexible instead, just because their bodies are just so massive. But if you think of kind of smaller animals like a squirrel, right? A squirrel is a very, very light animal. There's the squirrel's muscles are going to be a lot more flexible, a lot less stiff, and that's what kind of lets it kind of do all these kind of crazy things and jump all over the place and kind of bend, over backwards. Okay, and so there's kind of a lot that we can kind of do with this analogy, and it's something that we'll talk about kind of again as we kind of go through the different aspects of biomechanical dynamics. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's all we got time for today. So thank you guys. Thank you guys for coming in virtually. And so, I appreciate your guys' flexibility. I will be back in class on Wednesday. And so if you prefer coming in person, I'll be there on Wednesday. But the Zoom option will be available on Wednesday as well, just as usual. Okay. All right. So thank you guys for coming today. I hope you guys enjoy the rest of your day, and I will see you guys on Wednesday.